Many of our electronic devices today, from phones, computers, even our cars, contain tiny semiconductor chips with millions of transistors, and these chips likely wouldn't exist without one key company. ASML is the world's only supplier of advanced lithography machines. These machines used focused beams of UV light that pass through a translucent reticle to print transistors on chips the size of your fingernail. With high-energy UV light passing through it every second, the reticle tends to heat up during lithography. In an application that demands nanometer precision, even minor thermal deformations in the reticle can cause huge manufacturing losses in chip manufacturing. The semiconductor industry is nearly $1 trillion industry, and consumer and government demand is skyrocketing. The top 3 chip manufacturers, Intel, Samsung, and TSMC, rely on ASML's advanced machines to meet this intense demand. Even small improvements like this cooling solution will allow for an increased production and new innovations in this booming industry. ASML is seeking a new and innovative solution to their reticle cooling problem. Team Scrapstone is developing a solution that can dissipate a 100-watt heat load, keep the reticle at a constant temperature, hold temperature gradients to around 1 degree Celsius, and withstand the vacuum environment of a lithography machine operating at around a 10G acceleration. ASML's current solution uses water channels through a chuck that holds the reticle. While this achieves the desired temperature gradients on the reticle, it creates an unwanted vibration. After the design ideation phase, our team landed on a design utilizing 2 components, a vapor chamber and a cold plate. A vapor chamber is similar to a large heat pipe. On one side of the vapor chamber is the heated reticle. The heat causes the water in the wick to evaporate, and the vapor will rise and spread out through the vapor chamber. On the opposite side is our cold heatsink. On this side, the vapor will condense back into a liquid in the wick. The water then travels through the wick to the heated side by capillary pressure. The heat sink chosen is a cold plate. Chilled water is passed through an aluminum plate in direct contact with the vapor chamber. The water will pick up the heat from the vapor chamber and expel it through a closed-loop water cooling system. The main benefit of the vapor chamber is that it allows for heat to be uniformly spread out over the surface. With a more uniform heat distribution, water cooling can occur at a lower velocity, which will lower the vibration levels. With a concept in mind, various simulations were conducted to land on a detailed final design. Through fluid simulations, we observed that the vapor in a standard vapor chamber would move around too much during acceleration, and a fluid analysis showed that capillary pressure would be too low for a standard vapor chamber to operate successfully. To address this issue, we developed a segmented vapor chamber, which would limit the capillary pressure needed for normal operation. Our thermal simulations show that a vapor chamber with 15 segments can hold a reticle at a 0.15 degree gradient in the non-segmented direction and a 0.5 degree gradient in the segmented direction, which exceeds our targets. The expected thermal deformation of the reticle would be 675 picometers in the worst case. Simulations were also conducted to determine a cold plate design. A geometry of 4 channels, each with a 10mm diameter, a flow velocity of 1 meters per second, and its own inlet and outlet, produce the best balance of minimizing temperature gradients and minimizing vibrations. With this configuration, we predict a von Mises stress of 62 kilopascals, which is well under the plate's yield stress of 241 megapascals. Shown here is our final design concept. Next, a prototype was developed. The goal of our prototype is to validate our simulations and compare the temperature gradients of the system at rest and at acceleration to better understand the impacts of this high acceleration. The custom machine vapor chamber was mimicked by using an array of smaller heat pipes, and the reticle was substituted by a borosilicate glass. The cold plate was machined with 6061 aluminum stock, and a pump was selected that provided a flow rate of approximately 0.5 meters per second. When tested under a 75-watt heated wire, the reticle was able to maintain a temperature of approximately 48 degrees Celsius. The temperature gradient was around 7 degrees, much higher than expected. We believe the gradient is due to the uneven heating from the wire, so tests will be reconducted with an adhesive heater that will provide a more uniform heating. With static testing complete, the team will test the mechanism on a high-speed testing rig. By comparing the temperature profiles and gradients under both static and dynamic conditions, we can better understand the impacts of these high accelerations on our cooling system's temperature gradients. We will aim to share these results at the Capstone Expo soon. For chip manufacturers, our cooling solution will help reduce deformations in the reticle, thereby increasing production capabilities in fabs. This will also reduce waste in the microchip production cycle. For ASML, this effective solution will enable the company to spend less time addressing defects and instead focus on new technologies for more advanced chips. And for all consumers, increased chip production will lower prices and improve accessibility for phones, computers, cars, and even medical devices with the most advanced processor chips. Thank you for watching, and we hope to see you at the Capstone Expo.